And happy day, friends. We're going to go ahead and get started with a couple of reminders on PLC 9 for this week. Excuse me. We've got homework 4, and don't forget there's a quiz on homework 4 problem style. You'll have a little bit of fun with that one. So take your time to do that today, please, and we'll post up the lab on Friday, which is for me, that's tomorrow. And we'll go with some more heat and thermodynamics in the lab tomorrow. And from this point on, so this is the end of week 9, so we'll get week 10 in starting next week. And that means we're just about in the home stretch. And it's going to be flying past. We're going to get to second law of thermodynamics next week. We're going to get to some other stuff like heat transfer a little bit after. So I think expect celebration 2 sometime in like, I would say maybe like three weeks, maybe somewhere around there. And we're going to roll into modern physics, which is going to be a compendium of both special relativity and quantum mechanics. Little bits of both, just nuggets, because we don't really have a lot of time to put into diving deeply into them. But that's going to be a lot of fun, and I know I'm really looking forward to it. So after that, pesky little final, and then we're done. So off to summer vacations or summer break or whatever it is that we have going. But until then, we'll roll through this and we'll keep it going. Left off last time talking about kinetic, kind of the application of mechanics and Newton's ideas, what I would say are the 4A ideas mechanically, right? Momentum, second law, Newton's second law. And we applied those to a system of a system of a large number of small independent particles. Now, the number of that, the amount of stuff in the system was something I was trying to get across to you last time, in the sense that we have a mole of something being somewhere on the order of 10 to the 24th amount of particles, which is a horrendously large number. And when you get systems of that size, then you can have the ability to talk about average behavior. And ultimately, that is what we experience and what we are able to measure, because when you have a thermometer or when you have a pressure sensor or something like that, what is happening is it's interacting with so much, or it's interacting with so many things so quickly that it basically gives you the average of all of these interactions. So the idea from yesterday was that the pressure depends on the kinetic the kinetic energies of the molecules or the particles. And we're going to explore a little bit about the speeds, the speeds today's and the kinetic energies and things like that, as well as mean free paths and a couple of other mechanical quantities about how the gas particles might be traveling. But ultimately, we measure in terms of macroscopic quantities like pressure and temperature, we measure averages, statistical averages. And so that's why we're able to do things like, say, when in thermal equilibrium, we'd expect half to be going this way and half to be going this way, or there's no dependence on the direction, right? Every direction is equally important. So those types of mentalities are nice to take with us going forwards. So let's go ahead and take another quick look at some of the kinetics of the ideal gas. So I'm just gonna recap a few of the relationships we found yesterday or / last time. From our PV graph, if we have a constant volume process or if we have a constant pressure process, we found that heats added to these processes result in different temperature changes. So that we had for this situation, at constant volume, is this? Yeah, okay. At constant volume, we had the ability to say, well, because there's no work being done, then all the heat that we put into the system or take out of the system is going to result in a change in the internal energy of the system. So I used the situation of a rise in the temperature. So we add heat and the temperature goes up, but you could consider the opposite to be true, where I am removing heat by icing the system or something. Excuse me. And therefore, I am directly removing the internal energy via a heat transfer. When we do that, we have the molar specific heat at constant volume, which allows us to calculate what we think the rise in temperature is going to be for a constant volume process. And we found that this quantity, CV, was equal to 3/2 R for a monatomic ideal gas. Also was true for diatomics in a small temperature range, but ultimately what was funny is that the diatomics changed, and we'll talk a little bit more about what happens with that. So we have the amount of heat needed to increase the temperature of 1 mole of gas by 1 degree. Okay, so if you calculate 3/2 R, that's going to be something along the lines of about 12.5 joules per mole per degree centigrade. So you're talking about 12.5 joules to increase 1 mole of a gas by 1 centigrade. Or I'm just always a person who's heating things up. Or you could be alternatively cooling it off and removing that heat. And indeed, this is experimentally found to be true for the noble gases and some of other gases in a small temperature range. We'll talk more about that in a few minutes. This situation was a constant pressure process, and when we examined the constant pressure process, we found that I could take that 12.5 joules that increased the 1 mole by a centigrade in this case, but it would not increase 1 mole by a full centigrade here. It was not going to be enough to do that. So the constant pressure specific heat is larger than the constant volume specific heat. So the constant pressure molar specific heat in this case was called CP, and it equals, well, I think we found this, it equals CV plus R. In other words, it's 5/2 R. Okay, and that means that I need more heat in order to affect the same temperature increase when doing a constant pressure process versus a constant volume process. And all of this was kind of down to the idea that we had established that the energy of the gas was related to the kinetic energy, or should I say the internal energy of the gas is the kinetic energy of the ideal gas. So that we found that the internal energy was essentially equal to 3/2 nRT from our exploration into the collisions of the molecules, or the particles if you like, and looking at what was going on there. So one other relationship that we can come up with from this was that when we did do the pressure, we had the pressure relationship. The pressure was 2/3, let's see, I don't remember what it was, 2/3 of the kinetic energy. Yeah, so the pressure was 2/3 N over V times the average kinetic energy. let's see, I'm just doing this off the top of my head. Am I getting that right? Yeah, I think that's right. Where I'm utilizing the triangle brackets to mean an average. I used them last time to denote the vector components, but also we use them to use as the average. So knowing that we have the pressure and a relationship between the kinetic energy and the number density, we can also make a determination of the relationship between the ideal gas, which is how this internal energy came about. We can make an assessment between the ideal gas equation of state and this relationship here. So if I multiply the V over, I'm going to find that the P times V is that quantity, but it's related to the number, right? So this is N, which is the number of particles in the system, and this is the average kinetic energy per particle. So this N times KE is really, for an ideal gas, the total internal energy. So we really could write this as 2/3 internal energy. And that's kind of how we came up with this thing here at the top. All right. So now that we've kind of looked at some mechanical pieces to this, and we've talked about some averages, I want to delve back into the RMS speeds, and I want to delve back into the mean free paths. All right. So let's do this. Let's start with the RMS speed. Now, last time we talked a little bit about this, and I introduced it as an average, or as a way to do an average, which is, in other words, you take all of your numbers, you square them, you add them, and then you square root them. Or I should say you square them, you add them, take the average, and then square root them. So I just came up with a set of numbers here. Suppose that I took a bunch of measurements of some molecular speeds. Okay, so suppose that I have a bunch of V's, and I'm going to have a table of these speeds in meters per second, and we'll just call them 500, 600, 700, 800, and 900. Now, I want to compare the average, the literal average of this, which we can do because we don't have the problem of having negatives and positives. We just have a set here. But I want to compare what the average looks like to what the RMS value looks like. Now, in this case, I think it's fairly straightforward to see the average is going to be 700 because I've got 2 below and 2 above. So that is my average value. This is not a great example based on what we were using the RMS for, in the sense that when I talked about particle velocities and I had a coordinate system in which some were negative and some were positive, well, when we did the average of those, that average would come out to 0. And that's why the average is not useful in that case. In this case, it's a little bit different, but nonetheless, I want to now do the root mean square of this data set and look at what happens. If I do that, what I have to do is square each one of these and then take the average and then square root it. Right? So I literally am doing the RMS kind of backwards. It's really the SMR that I want to do here. If I find the RMS value, okay, the RMS value I would get by doing a, let me just get a little more room here. I would do this by setting up the square root of 500 plus 600 plus 700, right? I square each one of these. I take the average, and then I do the square root of it. So this is how to compute a root mean square from a fairly simplistic data set, right? It's the square, it's the mean, and then it's the root. If you do this, you come out with a 714. Is that what I got here? Yeah, 714. 714. So comparing to the literal average value, yeah, it's not the average value, but you wouldn't expect it to be, okay? Because I'm doing all this other stuff. It's a reasonably good indicator of the average. As you can see, it's not literally the average. However, it really helps when you have a data set with, say, equal amounts of positive and negative numbers. Because then the average value will be, well, it's not that it's going to be wrong, it's just not going to be useful, okay? Whereas this is a bit more useful. You'll note it gives a bit more weight to the higher numbers in the data set because this ends up a little bit higher than the average value. So these 800 and 900s, they weigh in a little bit more because they're bigger. Now, if we take a look at what the RMS value means in our sense of what the ideal gas is telling us, then what we can do is look at something like the kinetic energy here, right? If I take that kinetic energy, this is my average kinetic energy. I know that's going to look like 1/2 mv squared, but that v squared is an average, okay? Now, since we have the ability to say that this kinetic energy for an ideal gas is related to this expression here for the temperature, since I can say that this is equal to 3/2 nRT, I'm going to have to mess around a little bit with the variables here. Well, let's do this. I want to find out what's that. So how do we come up with an expression for the average squared velocity? If we do that, the halves are going to go away, and I'm going to have to divide this m underneath. Okay, so I'm going to get 3 nRT divided by little m. Now, if I want the RMS speed, all I got to do is square root this thing. But before I do that, I want to examine this n and this m real quick, because we can actually modify that to be somewhat simpler. And if you are someone who is familiar with the periodic table, I mentioned this last time, the number of grams per mole as an atomic weight. That's kind of what this thing is. This is the mass of, if I think of the mass of, well, in this case is the mass of one molecule, so I really would want to have capital N under here, really. If I wanted to do the total, yeah, that's why this isn't really going to work. Really what I want to do is have the total mass here. This is the total mass of the system, right? This capital M. And then I want this thing to be the system's number of moles. So if I can do a bit of fancy footwork and I can take that molar thing and pop it underneath here, then that'll be the basically the atomic weight of that species of ideal gas, right? That'll be some number of grams per mole. So I can rewrite this as something like 3RT over M, where this M, maybe I'll put feet on it or something. It's not the same as this M. This essentially is the atomic weight of the species that we're dealing with, because the system's mass and the system's number of moles are related by the number of grams per mole each one of the things weighs, right? So this is the system's atomic weight, or I guess I should say it's the atomic mass. We got to be careful though, because normally you'll cite it in grams per mole. We're going to need it in kilograms per mole in order to keep the units copacetic up at the top. This R, you'll probably remember. The units of R are going to be in joules, and that's where the kilogram comes in, per mole per Kelvin. The temperature we're going to need in Kelvin, because remember the rule of thumb about the temperature. If it's a delta, it's okay to have Kelvin or centigrade, but if it's a T by itself, it's got to be Kelvins only. All right. So in this case, we have an expression which is fairly straightforward for the RMS speeds. Let's go calculate a couple of them and see what we come up with based on different temperatures. All right, let's take care of this here. Let's do a calculation of the RMS speed. Let me just finish this off then. What we can do then is take this thing and say that VRMS is then the square root of all of that stuff. As a way to calculate it, all we really need is to know what molecular species we're dealing with and what temperature it's at, which is, that's pretty cool. That's not a lot to need to know to find the RMS speed. So let's calculate VRMS for hydrogen gas and air, which is mostly nitrogen gas. And let's just do it at room temperature. So room temperature, say, is 20 centigrade, right? Which should be around 293 Kelvin. All right, so for hydrogen, if I'm gonna just go in and see if I can calculate what this number is, because we're gonna interpret what the overall result is gonna be for these numbers. Let's look at the hydrogen VRMS. How would you calculate it? Well, you do 3, 8.31, and then the Kelvin temperature of 293 Kelvin. Now we need the molecular mass, or molecular mass, because it's the hydrogen molecule. So hydrogen has a mass itself of about 1 point, a bunch of zeros, and then like a 7 or 8 or something. And I've got 2 of those. So I'm going to have 2 molecular mass of hydrogen. Now that's going to be in grams per mole, so I need to include a conversion here to kilograms per mole. Square root of all of that. Okay, now if I do that, I get a number, and that number is pretty large. It's almost 2,000 meters per second, 2 kilometers, almost 2 kilometers per second. If I look at nitrogen, I'm going to find the nitrogen VRMS here. Same idea, same temperature. Molecular mass now of nitrogen, what is that? I don't remember. It's, looks like 14. And that's in grams per mole once again, so I'm going to do 10 to the minus 3. And square root of that. So I guess the molecular mass of air is around 28 grams per mole. That sounds right, yeah. I think that sounds right. Okay, if you calculate this number, it's going to be you can see vastly different than the hydrogen number, because the numerators are the same, but the denominator is much larger, right, by a factor of almost 15. So this number comes out to be slightly above 500. It's about 510. And the interesting part to this is that we have one of these gases in the atmosphere, but not the other. As you know, nitrogen is the 3/4 of the air is nitrogen, okay? We don't find hydrogen in the atmosphere. We find it bound up in water vapor, but as a gas by itself, no. And the same thing is true with helium. Helium does not exist in the atmosphere. So the question is why? And the answer lies in the interpretation of this number. The number of the VRMS here, this is a huge, I mean, not huge, I guess, but it's a pretty big number, okay? And it's kind of astounding to even think that at room temperature, these molecules are moving basically 5 football fields per second or something like that. That's pretty fast, okay? But look at this for the number for the hydrogen. And helium would be somewhat comparable to this, be a little bit less, but it'd be still up in the thousands. This number is kind of close to the escape speed from Earth. In other words, the gases, the molecules of the gas are moving so fast that they can leave Earth's atmosphere and escape Earth's gravitational pull. Whereas these ones are heavy enough to be held by Earth's gravitational pull and sink down here where we can breathe them. Well, we don't really need to breathe them, but we do. And they stay here, okay? And this is one reason Moon doesn't have an atmosphere, because its mass is small enough that its gravitational pull is not sufficient to even keep nitrogen there, let alone anything like this, right? It's way too fast. So the helium that we have in balloons that we use to inflate the balloons is actually not from the atmosphere. We don't have atmospheric hydrogen or helium, which, by the way, are the two most common elements in the universe. So the question of where does the helium come from? It comes from underground. All the helium that we have here on Earth to inflate balloons is due to radioactive decay, and it turns out that helium is a byproduct of radioactive decay of heavier elements, such as uranium, or bismuth, or osmium, or things like these heavy elements that radioactive decay causes them to break apart. One of the things they eject is a helium nucleus. So, nice piece of trivia to know for the next time you want to give or accept a helium-filled balloon from someone who's trying to give a helium balloon to your child, or you could try to give them to someone else's child with the information that this balloon is filled with the products of radioactive decay. Here you go. And you'll probably get some interesting reactions to things like that. But nonetheless, this is too fast for this species to stay in Earth's atmosphere. Now, I'm trying to recall off the top of my head what the escape velocity of Earth is, and I think it's higher than this, so I want to address that. I think it's like 6 kilometers per second, I think, is the escape speed. But this is only 2, so why is hydrogen still able to leave? This is a very interesting and ultimately useful way of thinking, and it was thought up by Maxwell, molecular. And ultimately also a fellow by the name of Boltzmann, who was able to derive it in a slightly, and give it more meaning, say that. The distribution of molecular speeds. So, in other words, when you calculate these VRMSs, and I alluded to this yesterday when we were talking about the momentum change of the particles hitting the wall, trying to calculate that pressure. These particles do not all have the same speed. Nothing, and in fact, you'd be hard pressed sometimes to even say that any of them have the RMS speed, right? It's like having a big sample, a big data set, and then taking an average, but no one actually has an average. That number does not appear in the data set. It's just the average, right? So these numbers represent the speeds of the gas particles, but not all the gas particles have these speeds. So what does the distribution of speeds look like when you're talking about, well, are these, do a lot of them have a speed that's kind of around here? Yeah, they do, but some have slower and some have faster. Okay, so this would be, for example, this is going to be a distribution, which means it's a relative number axis here. So this is just a number of particles that may have these particular speeds. And here's the speed. Now, this is a pretty interesting plot, and I'm probably not going to exactly reproduce it, but I'm going to give it what it's supposed to look like, and it's supposed to look like this. And the tail is a bit too long there, but I'm going to extend this axis so that we have a little bit more room out here. And I'm going to pull this down here like that. Okay. Okay, so it looks something like this. It's a relatively complicated function. It's something like a quadratic multiplied by a dying exponential, which is also quadratic in the exponential. But nonetheless, the form of it doesn't concern us right now. What concerns us is what the meaning of particles that have speeds greater than the average or / the RMS speed, what that means. So in terms of, let's see, I wrote down where I put these things, did I? No, maybe I didn't. No, okay. So I want to say that the most probable speed is the one right at the very top. This one here is the most probable, because the highest number of particles have that speed. Okay, so that's known as the most probable speed. You can see that because of the tail on this thing, the average is going to be slightly skewed to the right a little bit more. So the average, I'm kind of making up where these things are, but I think I'm getting the order correct. So let's say the average, I'll do this in a different color. Let's say the average speed is somewhere over here. But you know that the RMS speed is going to give greater weight to higher numbers. So the RMS speed is going to be still further over here. All right, so there are different ways of representing the average of the speeds, okay? But I want to talk about the physics of what's going on here. And I want to talk about what this graph, or what this distribution is useful for. It's useful for it as a mentality, okay? So if the RMS speed of hydrogen is 1900 meters per second, just say 2000, right? So it's 2000 meters per second. Look at how many of these molecules, how many of them do we expect to have a speed greater than that? Quite a few, right? Quite a lot. And this is typical of every system, of every system in which you have a large number of distributed speeds. So for example, take a glass of water, right? Just a regular, ordinary, room temperature glass of water. And you put it down here, and you come back in a couple of days, and it's gone, right? There's nothing left in it. And you'd say, how can that be? I know, because I've taken physics, that the only time that water can change state is at the boiling temperature. Well, that's not totally true. We have the evaporation, okay? Evaporation means what? It means that molecules of water are leaving the liquid state and going out into the gas state. Okay, how do they do that? They have a speed out here that allows them to move slightly quicker than the average of the temperature of the water in the glass. They move faster, and therefore they're able to leave. Okay? What does that do? It cools the glass of water down. Why? The temperature of the water has gone down. The temperature of the leftover water in the glass has decreased. Why? Because you've just ejected a quote-unquote high speed and therefore high temperature molecule of water from the glass. That took a lot of energy away, which means the internal energy of the leftover water dropped. And that means the temperature went down. Okay? And so if you think of the same idea, so that's what evaporative cooling basically means. It means that you're looking at the ones, the molecules in the sample that have speeds out here and thus are able to, excuse me, are able to leave the glass of water and evaporate into the air. And what that does is it ends up cooling the whole thing, which means that this whole curve, the average of all, whichever one you want to talk about, the RMS speed, go down. And then this curve gets a little bit more like this and then goes like that, which means that you still have ones out here, right, that are still faster. Now you've got a slightly cooler glass of water. What happens? Heat comes in from the environment, heats it back up, it resets the curve, more of the water evaporates until there's none left. Okay. Same thing happens with the hydrogen, right? The hydrogen has a lot of population out here in the tail, which means that they are able to leave. And what does that do? It moves this thing around, it resets, because ultimately we are operating in at least near or at thermal equilibrium. So as soon as that happens, what it does is it elevates. If I lose some of these molecules out of the sample and they're gone, right? If I'm talking about hydrogen, they're gone now. They're not a part of the atmosphere anymore. The atmosphere cools slightly, okay? Which means, or at least that part of the atmosphere cools slightly, which means it takes in heat from the other parts, which resets this curve, which means that some of these molecules that were down here are now getting elevated to up here. I'm getting more of the molecules to keep moving away, and I eventually lose all of them via this process. So we don't have atmospheric hydrogen nor helium due to this. And also it's the reason that, and you can also talk about what's going on over here. This is the reason. And now I don't know how it is where you all live, because I don't know you or where you live, which is good. And I will tell you that I live in Watsonville, in which during the December and January months, we often will wake up to a frost. Not a freeze, a frost, which means that there are some bits of solid water around. In other words, what's happened is, because the temperature, right, this is the RMS speed is basically telling us what the temperature is, but there's a significant fraction of these things below that temperature. It's not freezing outside. You will find that it's typically around high 30s, maybe 38 degrees Fahrenheit, and you'll start getting frost. And the reason you're getting frost is because you've got all these down here which are moving slower than the average, and therefore if it's not a freezing temperature, these ones over here are still able to basically freeze. But they don't all do it, right? It's just ones that are down in this part of it. So the real interesting part to this plot are the tails, right? And where are the tails in relationship to the macroscopic behavior? This is the thing we measure because we measure the temperature. So what's happening out there and what's happening back here? That's the interesting part, or at least for me. So anyways, that is known as the Maxwell-Boltzmann distribution. I should probably give you their names as they will become more talked about as time goes on. Maxwell-Boltzmann. All right. Good. So let's do this. I was going to, so we've done the RMS. Okay, I wanted to do this. We wanted to talk about mean free path. Do I really want to talk about mean free path? Yeah, let's do it. Okay, here's your demonstration for today. Big tube. Representative of the distance a molecule would travel, or I keep saying molecule, but a gas particle would travel prior to having a collision with another one, okay? As we've talked about, the system of the ideal gas is, in our minds, modeled as a set of independently moving bouncy spheres, right? Billiard balls, okay? And that means that when they hit, they bounce off one another and they move a certain distance before they hit again. And that's what I'm talking about here. That's the distance that they move. So they hit something and they move a distance and then they hit again. And the distance they move without colliding is this, on the average, obviously, right? This is all we can do with sample sizes of this nature. All we can do is talk about the average. So this is the mean free path. In other words, it's the path that they can take without colliding. Let me sketch this out real quick and just put a bit of physics to it. I don't want to spend a lot of time because I want to move on to some other stuff, but the idea of the mean free path is that it answers the question, how far do these things, how far is it between collisions? All right. So essentially, I'm just going to call this something like an L. I'm going to call this L. The mean free path is L. So what we have here are, just for a drawing's sake here, here are some ideal gas particles, and here's the one that we want to look at. Let's do this one in red. Here's the one we want to look at. So what I'm interested in is how far on the average does it go between collision? Because right now it's going to go here, and then it's going to hit off this one, and then it's going to hit off that one, and then it's going to hit off this one, and then it's going to hit off that one, and then it's going to hit off this one. So you can see that the path is going to be different. The free path between collisions is different, right? This is slightly shorter, this is a little bit longer, this is much longer, this is shorter, this is longer. So we need to take the mean of these, okay? And then figure out approximately how far is it. So that means I'm gonna have to change where I'm doing this. Let's do this over here. So it's going to depend on, okay, how far does it go? First of all, just at the speed it's going, okay? In other words, if I take a certain time, this is the time between collisions, and it's moving a certain speed, okay, it's going this distance. It could go this distance. All right. Now, how likely is it that there is a collision, right, in this time interval? All right. So I'm going to divide by the number of collisions that happen in this time interval. Oh, I said this is the time between collisions. No, take that back. This is just some time interval. What I want to do is figure out how many collisions happen in this time interval. All right, so this is like number of collisions in delta t. That's what I want to do. I want to talk about how far did it go in some time interval and talk about how many collisions it had so that I can get a statistical average, right? The good news here is we've already calculated this quantity right here. We did that in the analysis of the momentum and the getting of the pressure of the gas when it hits the wall. So that was the thing I called capital N sub collision. Okay, so that we can just use that, and that is N over V times V delta T. Right? Remember that this is the number density multiplied by the distance the thing goes. But remember, I need to multiply, this is the number of collisions, so it's like the number of other things that it has to hit in that path. So what you can do is you can kind of think of this thing as it has a collision with something if the diameter of it hits any part of the diameter of another one. So for example, if I consider a particle right here, it's going to miss that one because the center to center distance is more than a diameter. Okay, in other words, the distance from here, the center of this one to the center of this one, is larger than the diameter of one of these particles. If the distance from between the centers is larger than the diameter, they're going to miss each other, right? That's 2 radii, basically, right? Right? If they were touching, I'd have one like that, I'd have one like that, and I'd be looking at the center to center distance as being 2r. That's the same as a diameter. So if the center to center distance is further than the diameter, they miss. If it's that or closer, they hit. So in order to find the volume of this, remember last time in the analysis, I just multiplied by some area, which I then divided off to find the pressure. That area now becomes the area of that circle, pi times d squared. Now you'd say, wait a sec, that circle should be pi times r squared. No. The circle is 2r in size. So really 2r is equal to the diameter. I'm doing a circle of radius, one of the diameters of these particles. So this is pi d squared. It's not pi r squared because that's not the circle I'm interested in is one of that radius. That's the radius of the circle I'm interested in. So that's why it's this, right? And so the mean free path essentially depends on, it's like a tube, right, like this, which just connects between each of the molecules. And you can notice that we get the cancellation that we got before, and et cetera, et cetera. I'm going to get a V over N or a 1 over N over V. And if you look at it from an ideal gas perspective, this N over V here is equal to what? This would be equal to the pressure divided by R times T. Is that true? V. Yeah, so what this ends up being
is the mean free path ends up depending on the temperature directly, which is a funny thing, and it depends on the pressure inversely. So let's examine that and see what we get. So if the temperature goes up, it's saying that the mean free path goes up. And that maybe kind of makes a bit of sense, because if I keep all the other things the same, in other words, the number density, right, and all of that stuff, but the temperature has gone up, then it's going to travel a further distance in the same amount of time because the speed is higher. So higher temperature means longer mean free path. Okay, that makes sense. That's kind of like, no, I was going to say that's kind of like having a candle and then putting the candle out. Then you smell the smoke pretty quickly because it's at slightly higher temperature than the room, versus if you just opened a jar of something that smelled like perfume or something like that. If you just open that up and set it down, eventually you would smell it, but not as quickly as a candle. So the temperature going up means the mean free path is longer. The pressure going up means the mean free path is shorter, but that kind of also makes sense because if I've compressed things, they can't travel as far, right? It literally means the distances between things are smaller. They compressed it. So they're hitting each other a lot more rapidly. And that means that I've got a shorter mean free path. So anyway, there's a little bit of reasoning on the mean free path. I don't think we're going to do a whole bunch with this in the future here, but I just wanted to mention it because it is kind of it's a useful thing to think about. This is much more useful, but that's okay. I want to go back and talk a little bit more about the changes in the molar specific heats. Now, I mentioned this last time, which is that which was that the specific heat changed with temperature for some gases. And what we found was that for diatomic gases, the molar specific heat could increase above the 3/2 R value. Now, I want to make clear that the diatomic gas also starts out here. It starts out here at 3/2, but eventually as you warm it up, it jumps. And then as you warm it up, it jumps a little bit more. Okay. So this got down to a little bit of the activation of these modes of having energy. I think we also talked a little bit about this, the idea that the diatomic molecule is the barbell. And therefore, when it jumps up, it's activating the rotation of the molecule. And when it jumps up again, it's activating the vibration of the molecule. All right. So here is a quick and easy way to think about trying to calculate molar specific heats. Using what I left you with, which was called the equipartition of energy. Now, the equipartition of energy is, as I said at the end of last class, it's basically the idea that everything is equally probable. Okay, in other words, if I'm filling up a 3/2 R, in other words, suppose I have a monatomic gas or a diatomic gas that is not free to rotate yet. It can have kinetic energy in each of the three directions. And there's no reason why each of those three directions shouldn't be equal. Okay? Well, once we allow the diatomic molecule to then start rotating, now there's no reason that those rotations shouldn't be the same and carry the same energy as the translations in space. Okay? So the idea of equal partition of energy is that the energy is divided equally amongst any way that the molecule can have the energy. It just so happens that we have to count how many ways can this molecule have energy. Okay? So this is the equal distribution of energy. I forgot the word distribution. This is the equal distribution of energy amongst what are called the modes. Okay, and the modes are ways of having energy. So for example, with a monatomic ideal gas, it's just a ball. It goes this way, has kinetic energy, goes this way, has kinetic energy, goes this way, has kinetic energy. Those are modes, right? It's a distinct different direction, and therefore I can have kinetic energy this way, and this way. Those are three modes. Okay, so this is a way of having energy. I was going to say storing, but I'm not going to say storing, I'm going to say having. It's like the energy bucket, right? It has, the monatomic ideal gas has 3 energy buckets, they're all equally full. The diatomic gas that rotates has 5 energy buckets, again, they're all equally full. And so our goal here is to try and figure out how to count the modes. Because ultimately, the way I've been telling you about this, you can probably see that the molar specific heat at constant volume is nothing more than the number of modes multiplying 1/2 R. So we can just say that CV is equal to the number of modes times 1/2 R. And therefore, all we need to do is count the number of modes. All right? So, in situations like this, you'll find more or less explicit situational setup sentences, meaning here we have a sample of diatomic gas that is free to rotate but not vibrate. Okay, so that means it's here. Here I have a monatomic ideal gas. Well, then it's here. Okay, so it's the idea of counting the modes that let you know how much the specific heat value is. Okay. So these number of modes, which can be broken up, right? Translation is 3. There's always 3 translation modes because we have 3 space. At least we live in 3 space, at least as far as we can tell. This is not string theory, so we're not in 10 dimensions or 12 yet. Translation is 3. Rotation depends. You have to count these. Okay? If it's a diatomic, then it can have 2 of these. In other words, if it's diatomic, I can go like this, or I can go like this. But I cannot go like this. I don't know if you can even see that. I'll take my bottle here. It's not this. Okay? It's this or this, but not that. That's why there's only 2 rotation modes for a diatomic molecule. Now, is that to say, no, it can't rotate that way? No, but it's to say that the energy necessary for it to do that is basically exactly the same as moving around. So we don't excite that mode. So rotation is 2 if it's diatomic. If, for example, it turns into, you have a molecule that looks like this, well, now how many do you have? Well, now you've got one that can have it go in in the, right, like this, in the plane of the board. It can go this way, around and out of the board, and then it can go this way. That's 3. So if it's got a more complicated structure than just the barbell, then 3, because there are 3 axes around which you could rotate. Okay? So this could be 3 if it's polyatomic. In other words, anything more than 2. Vibration is once again 2 if it's diatomic. In other words, how does the molecule have energy? Well, it has energy in the relative kinetic energy between the 2 atoms themselves, as well as the spring potential energy due to the bond, right? So this is a situation where this is 1 for kinetic energy and 1 for, I'll just say, potential energy. All right, so this is our first potential energy way of having energy. All the rest of these are kinetic. Okay. So watch the wording. The wording will tell you, oh, it's a diatomic molecule, but it's not vibrating. Okay, well then this is not in play and we're at 5 halves. Okay, and that, incidentally, for air is the most common situation. Air does not, air can move and rotate, but at room temperature, doesn't have enough energy to vibrate. So it doesn't engage those modes. Okay. I just want to see if we can get away with a quick example here, and then I think we had best finish up. So let's do this. All right, I'm going to take an example here, and I've got a PV graph in which I've got a gas which I'm going to take from one state to another state. Let's say it's A, B, and C. And I'm going to go this way, like so. So let's assume that I've got a 1 mole of an ideal diatomic gas that will rotate. In other words, no vibration. And I know what these pressures and volumes are. Okay, I have numbers for these. We're going to do 5, 2, and 2 and 4. So we'll do 4 and 2, and we'll do 5, and we'll do 2. All right, so this is going to be in kPa, and these will be in cubic meters. All right. So our first question here is to try and find the internal energy change between A and C. Between A and B. Okay. What's the internal energy change from A to B? And then let's find it from B to C. All right, so this is where the kinetic energy relationship comes into play. Remember that for the ideal gas, I'm going to have the internal energy being N times CV times delta T. So I was telling you about this last time. We were using the 3 halves last time. But now that we are here counting modes, if I remember that even though I'm talking about a constant pressure process A to B, I'm still going to use this because this is just a placeholder. This is just a quicker way of writing what the number of modes is times 1/2 R. Okay, that's all this is, because that's what the internal energy is, right? It's the number of modes times 1/2 R times the number of moles in the thing, and then the temperature. And if there's a change in the temperature, a change in the energy. So here in this case, what we have is that I'm going to have 1 mole. I'm going to have 5/2 R for the CV. Yes, I know it's a constant pressure process, but this is just the energy. And I'm going to need a delta T here. Delta T, NR delta T. So I'm going to leave the delta T here because I don't know what the temperatures are. Now I have one of two possibilities here. I can go calculate the temperatures at each one of these places because I know the pressures and the volumes, and I know the number of moles. Okay, so that I could calculate the temperature at A, B, and C. What I'm going to do, though, is I'm going to look at, well, wait a sec here. I've got an N, and I've got an R, and a delta T. So if I have an N, an R, and a delta T, that should equal delta in PV. Okay? In other words, I'm taking my ideal gas equation of state and looking at, well, what if I delta this side? I need to delta that side. Therefore, if I choose NR and delta T, I can replace them with delta in PV. And that means I can change this to being 5/2 of delta in PV. But you'll notice for this first situation, and by the way, that's not delta in P, it's delta in PV. You'll notice in this first situation that P is constant. So for A to B, this becomes 5/2 P times delta V. Then when I do B to C, it's going to become 5/2 V times delta in P. Okay, so I can use this relationship to figure out what the change in energy is going along here and going along here. Okay. So that's a shortcut way of doing the temperature. Instead of going to figure out the temperature in every place, I know that I'm going to have nRT in there anyway. So just use the ideal gas equation state, and that can make it easier. Let's also see if we can find the heat transferred. Let's see if we can look at how much heat's going to be transferred in a situation like this. And then I think we're going to have to be just about done. So find how much heat transferred. Again, same idea. A to B and then B to C. Well, in this case here, A to B is a constant pressure process. So now is the time, QA to B, I can use N times CP delta T. And that delta T, once again, I'm going to do the same type of game I did down here, because CP, remember, for a constant pressure process, this is CV plus R. Therefore, in this situation, this is 7/2 R. Now, I want to just make sure that I'm clear with this, and that is that when I have a monatomic ideal gas, and I have a CV of 3/2 and a CP of 5/2, those physically are different than having 5/2 here in a diatomic case, because I've got diatomic rotation. And so you just have to watch what you're doing with how you're using these things, right? This is going to end up being N times 7/2 R times delta T from A to B. B, which ultimately I'm just going to be able to say is delta PV from A to B. Oops, A to B. And then I can do it again B to C, but B to C is a constant volume process. So in QB to C, now I'm going to use the constant volume specific heat, and I'm going to find what I expect to have happened, which is that the internal energy change B to C should equal this number. And it does, because NCV delta T would be the internal energy change from B to C. Okay? So I can find whatever that internal energy change is and say that that's the heat transferred from B to C. All right, well, I'm gonna go ahead and say that we are just about done here today. So that's gonna do it for this week. We will finish off a few odds and ends on this on Tuesday of next week, and we will then start transitioning into second law stuff. Now, homework's due today, so please make sure that you submit that and take the quiz today. PLC is for tomorrow, so please be sure we have that. And I will get homework 5. I'll get that posted and we can get going on it. And it will involve a lot of kinetic stuff and second law of thermodynamics. So in the meantime, I will see you back here Tuesday. We'll have lab. I'll post that up on Friday. So until next time, I guess that's it. Happy weekend, and I'll see you next time.